All right. Well, so I'll get PA5 graded tomorrow and or Sunday, and I will give you feedback. Um, I've gotten comments from a few students saying that they were pretty unhappy with what they managed to do on PA5. This was an ambitious project. Okay, this was very challenging by design, and I did this because it's a chance to take a number of different concepts, a number of things that you've learned, and try to put them together into a pretty large scale kind of major project, right? And I didn't want to tell you up front, don't worry if you can't get it done, because I want people to work on it, okay? But grade wise, it's one grade, and there's partial credit and all that kind of stuff, so don't worry about that. But the people that I worked with during office hours, the people who talked to me about their code and asked me questions about it and stuff, I'm seeing lots of light bulbs. Okay, I'm seeing connections being made, deepening understanding of working with objects and also how these pieces go together, and that's really the goal that I was after with this assignment. So whatever you got working on it is fantastic. Don't feel bad if you didn't get your clicks on one screen to mirror on the other one, or you couldn't get communication working or something like that, right? Whatever you got out of it is good. And I'll try to give you specific feedback if you didn't get the thing finished, and we should definitely talk about it, right? You'll encounter assignments down the road in other courses where you're dealing with multiple processes and networked communication and so on and so forth. So it's all good stuff to have been exposed to and to understand as well as you can at this point. So anyway, I'll give you specific feedback as I grade it, but it'll be a couple of days for that. All right, let's talk more about multiple processes and the kinds of things that can happen and that we need to think about. We talked about semaphores, about using a lock or a flag so that if two or more processes want access to the same thing, you can control that by using a flag. And basically the first process that wants to access it will check to see if the resource is in use, and if it's not, it will set a flag saying it's in use and then start using it. And this is set up through, it can be just a Boolean variable somewhere, and the trick was how do you control it so that while you're asking if, hold on a second. All right, how do you set things up so that while you're asking if the resource is in use and you find the answer is no and you set a flag to say I'm using it, how do you prevent somebody else from sneaking in there and inadvertently doing the same thing? And so that was the idea of using atomic operations, right, where this read modify write could not be interrupted, and then you could know that you had exclusive access. All right, so there's other issues that we need to worry about sometimes. So there's this notion of deadlock and Livelock. And these are basically situations where, for some reason, processes that are trying to execute cannot execute beyond a certain point. They're stuck in their progress. Okay, and typical example would be, I'm waiting for two resources, you're waiting for two resources, right? So process 1 is waiting for resources A and B, process 2 is waiting for resources A and B. And process 1 has gotten A and process 2 has gotten B, and now this process is stuck here until it can get a hold of resource B. which is being used by the second process. Well, this second process is not going to release B until it's done what it has to do, and it can't do that until it gets resource A, which is in use by process 1. So they're mutually waiting for something that the other has, and neither will relinquish their hold on what they already have, and so they're stuck. Okay? You encounter this in daily life, when you're walking down the hallway and you're coming down this way and somebody's coming towards you, and suddenly you're face to face with another person, right? Now one approach is to simply stand there until the other person moves, and sometimes that works and sometimes it doesn't. Now, if your whole algorithm was just, I'm going to stand here until the other person moves, and if their algorithm was exactly the same, guess what? You're never going to move from that spot. You're going to be there forever. That's a classic deadlock, right? I could continue if this person was somewhere else, but they can't go anywhere else because I'm in their way, right? And I'm not going to get out of their way because I can't move because my path is blocked. Okay, now in practice what happens is, you're face to face with someone, so one of you moves to the side, but what happens more often than not, while you're doing that, the other person moves to the side, and now you're deadlocked again. And so you say, okay, well, I'll go over here, and for some reason, at the same moment, the other person makes the same decision and comes over here. And now you've got two people, and they're just going back and forth, side to side. It's not exactly deadlock, because the system is changing. You're moving forward. Your algorithm is continuing to execute steps, but you're not getting beyond the point of, being right here in the hallway. You're trying to get down here. And you just keep bouncing between these two states. Okay, that's a Livelock scenario. And both of these things are fairly common if you're not careful in programming when you're dealing with two or more threads. So it's been known for a while that these things can happen, and people have talked about them and tried to figure out how to deal with them. And so Dijkstra, who we sometimes talk about in discrete structures, Dijkstra's algorithm for finding shortest path through graphs. Dijkstra was a computer scientist, mathematician in the 50s, and he posed a thought exercise to help study these questions of deadlock and livelock and starvation, where you don't get access to a resource and so on and so forth. So he created this thought problem called the dining philosophers. Okay, and you'll certainly see this again in other courses. And we're just kind of touching on these subjects, but these subjects, threading and sharing resources and semaphores and so on, are part of courses like operating system courses or system programming courses, things like that. So we're just kind of doing a first pass on these. Here's the setup for the dining philosophers problem. You have 5 philosophers sitting around a table, and in the middle of the table is an infinite supply of food. So these might be noodles, and in between each pair of philosophers is a chopstick. And philosophers do 2 things. They eat and they think. And we want to simulate the behavior of this table of philosophers eating and thinking. And so here are the rules. So first you're going to think a random amount of time. And then you're going to try to eat. And to eat, you're going to acquire a chopstick. And then you're going to acquire a second chopstick. And then you're going to eat for a random amount of time. you're going to put down your chopsticks. And this is representative of multiple processes sharing resources. Okay, and so the challenge is to try to figure out algorithms that these philosophers can follow, so that everybody gets to eat, right? So you don't have starvation, which is where there's one or more processes that never get access to the chopsticks, so they never get any food. So you're trying to avoid starvation. You want to allow these philosophers to eat and to think. Well, thinking is easy, right? It's just put down your chopsticks, go back to thinking. But it's getting the chopsticks, okay? And you can only take chopsticks that are adjacent to you. So this philosopher is going to have to use these 2 sticks. This philosopher will have to use those 2 sticks, and so on. So we start to think of algorithms that would allow these philosophers to eat. And so a first algorithm might be, check for left stick. If not available, go back here, check for the left stick again. Otherwise, pick up the left stick, and then check for right stick. If not available, go back and check for it again. If it is available, pick up the right stick and then eat. And then, there's other steps that we don't have to list right here, but when you're done eating, you put down the chopsticks. Maybe you clean them if you're nice, and so on and so forth. But here's the start of the eating algorithm, right? And it's a straightforward algorithm, but it's prone to deadlock. So suppose all 5 philosophers decide to eat at the same time, right? Each one is going to pick up the stick on their left, which means the sticks will be assigned to philosophers like this. And then each is going to check for the stick on the right. This one's going to look and say that stick's not available. This one's going to look and see that stick's not available, and so on. And all 5 processes are going to be sitting right here in step 3. Just continually checking to see if the stick is there. And since none of them can eat, none of them will proceed to step 5 and then proceed to the steps where they put down their chopsticks, and that's it. The system is hung. Okay, and this is the case where you have code running on a server, and there's a database, and people are coming in and making requests, and all of a sudden at one point nothing is happening. Right? You go to your website and there's no response from it, and the system is hung. Okay, it's in a deadlock state. So you could, and you can randomize some things. And you could say, okay, so check for the left stick. If it's not available, wait a random amount of time, and then check for the left stick again. Right? So let's change this. Check for left stick. If not available, go back up here. Check for the right stick. If not available, I'm going to go all the way back to the beginning. Otherwise, pick up left, pick up the right, and eat. So now we're not going to pick up the sticks unless we know both of them are available. So what's the problem with this algorithm? Is there a problem? There's only 5 of you in the class, so this is harder. But throw out a guess on a chat window or use your microphone. Is there a problem with this algorithm? Or rather, there is a problem. What could it be? Yeah, someone could have picked up a left stick while checking for a right stick. Exactly. Right? So I'm going to look over here, and I'm going to say, yep, there's a left stick, and I'm going to look over there and say, yep, there's a right stick. But while I'm doing that, this previous philosopher had just checked the left and checked the right, and now they're picking up those sticks. Right? And in between the time that I looked for the left stick and saw it, and I looked for the right stick and saw it, the left stick disappeared. And so when I try to pick up left, I'm going to be blocked, right? And I'm going to be stuck. And this is the non-atomic business, right? If I could guarantee that nobody was going to touch the sticks while I was doing these things, right? Okay, everybody freeze, nobody touch the sticks. I look over here, see a stick, look over there, see a stick, I pick them both up. That's going to work great, right? But if we don't have that kind of locking, if that looking and taking sticks is not atomic, if something can happen in between, then we have the potential of acting on stale information, right? We're picking up the left because we decided the left was available up here, but between that point and here, the situation has changed. So that's a problem that can happen. And so we could say, you know, check the left, pick up the left, check the right, pick up the right. And we could say that if the right is not available, put down the left and go back up here. Alright, so your algorithm, pick up the left, check the left chopstick. If it's available, pick it up. Now check for the right chopstick. If it's available, pick it up. If not, put the left chopstick down and go back to the top and wait a random amount of time. And that can work, but it can also lead to Livelock. Because if these philosophers happen to be, you know, synchronized in time, they might all check the left, see that it's available, pick it up, look for a right chopstick, see that it's not available, put down their left chopstick, wait a random amount of time. While they all wait exactly 5 seconds and go back to the top, they're going to keep doing this. They're going to keep picking up one stick, looking, putting it down, waiting. And it's a Livelock situation. So how could we deal with this? What are some ideas for algorithms that would actually let these philosophers eat? This is useful when you have a dinner party and you've got very logical friends coming over and you want to make sure they can all eat. Well, suppose we identify these philosophers and we give them each a different algorithm. Suppose we say philosopher A is highest priority. And so if philosopher A wants to eat, whoever has those chopsticks has to give them up. And then after 5 minutes we say now philosopher B is the highest priority. Right? We could make a scheduling system. Somebody suggested getting rid of one. I think even if you have 4 philosophers and maybe even 3 or 2, you still have potential problems. But the problem definitely changes based on how many of these processes you have in parallel. So that could definitely change the situation. If you can identify the philosophers or the processes, right, you can do some kind of scheduling. So this is when these two eat, and this is when those two eat, and this is when these two eat, and so on. Okay, that's also similar to having a wait person who assigns chopsticks to people. So this person could say, okay, here's your 2 chopsticks. B, you're going to have to wait. C, here's your 2 chopsticks. And D and E, you're going to have to wait. And so you could have 2 people at a time eating like that, but you need a centralized control. Sometimes that's feasible, sometimes it's not. So something like a client-server situation where you have one client taking care of requests from multiple servers, one server taking care of requests from multiple clients, that server would have knowledge of all the processes being serviced and might be able to make decisions about scheduling. So that could work. It's harder when you have completely independent processes and no central control. And it's not too bad to come up with an algorithm that works most of the time, but there's always potential for some peculiar timing to arise in just the right way where things get deadlocked or live-locked. And it's a notorious problem when you're dealing with multiple processes. So like designing an operating system, right? This is sort of the quintessential example. You have hundreds of processes sharing a small number of resources, and these kinds of problems can occur. Sometimes when your program crashes or your machine crashes for no apparent reason, it's because things just lined up in exactly the right way or the wrong way, and something like this happened. So we can deal with knowing, if a chopstick is available by using a semaphore, right, or something that like a flag that basically says, is this available? And you need to atomize, that process. So check to see if it's available, and if it is, take it, right? And you need to make sure that in between the time you check and the time you take it, nobody else has taken it. So this check and take needs to be atomic, right? It's basically a read modify, right? Check the flag, and if the flag says the stick's available, modify the flag saying it's been taken, and then take the stick. And that works well for some situations. Okay, but there's other situations where that's really not ideal. So suppose we were just using a bunch of Boolean flags. So we have a flag called, left stick available, and a flag called right stick available. And so we could say something like, while not left stick available, and we'll just sit there and wait. And then once the left stick is available, we'll say set that flag to false. So wait for the stick, mark the stick as in use, and then continue with whatever we're going to do in our algorithm. Take the right stick or whatever, right? So this can be a problem. While the left stick is not available, go back and check if the left stick is not available, right? This is a really, really tight loop. So if you've done 270, right, in pick processor code, this would be like move file to file, left stick available into the W register, and this might be, wait 1 and branch of 0, wait 1. Okay, so it's 2 lines of assembly language code, and you're just looping back and forth here. Whole lot of CPU usage there. Okay, and if every process on the system that was waiting for something to happen was doing this, your CPU would be running really, really slowly. Okay, so my system right now, I have 330 processes executing. And most of them are in a state of S, which is sleeping. It means they're waiting for something to happen, right? But if all of these processes were executing a CPU-bound loop like this, the machine would be dragging. So this works great in theory for checking and setting a flag, but we need something more nuanced, something that doesn't consume the CPU time that this does. And one thing that does this is something called a condition variable. And you have condition variables in Java, you have them in C, you have them in most languages, specifically to deal with this kind of situation. And the basic setup for a condition variable is you have a pair of functions or methods. You have something which is basically a wait and something which is a signal. And there's arguments associated with this, but basically I could say I am waiting for, some resource. I'm waiting for some value to be set to something. I'm waiting for some condition to be satisfied. And you can have multiple processes or threads, each waiting for this condition to be satisfied. And whoever is responsible for whatever is, affecting this condition, for example, you want to have access to a printer, right? So all of these processes are waiting for the printer to be available. Well, there's one job, which is the print daemon, right, which is printing, and when it's finished printing and it knows the printer is available for some other process to use it, it can say send a signal. And the signal is set up so that it will pick exactly one process that's waiting for that and tell it, hey, this thing is available. And only one of these processes will be woken up and told that, and it will go ahead and it will take claim to the printer and it will go ahead and start sending its print job. And when it's finished, the thing that's controlling the printer will do another signal, and a different process will now be told, hey, that resource, that condition you were waiting for is satisfied. And so this is a mechanism you'll see a lot when you look at things related to threading and multiple processes and controlling access to a resource that's common to multiple threads. It's a condition variable. And like semaphores and all these other things, these are usually implemented pretty close to the hardware level, right? Because it's got to be efficient. And this is the kind of stuff that's going on inside Swing. When you make a listener for a mouse event or a key event, right? You're not sitting in a loop saying, has a key been pressed? Has a key been pressed? You're sleeping. Okay, your process is off in some other state that the operating system has put it in, with the understanding that when this event occurs, you're going to be woken up and told about it. And so all of these sleeping jobs, right? There's one job that's running, that's the top command, okay, which is what's displaying this. All these other jobs that are sleeping are hanging out waiting to be told that something has happened. Alright, so let's look at some other stuff. So let me show you some weird stuff that can happen with threads. Let's make a threaded class. So I make a class called T5 that extends thread. Alright, I'm going to have a Boolean variable called done, which I'll initialize to false. I'm going to make a public void run, which will execute when I call the start method. And I'm just going to sit here in my CPU bound loop waiting for the done flag to be set. And after that flag is set, we'll just print a message saying we're done and goodbye. I don't have to do that. Alright, so there's our thread. Basically just hangs out in a loop waiting for the done flag to be set. And once it's set, it will go ahead and print a message and we'll just exit. I'll put a return down here just to be explicit, but it'll return anyway. Alright, so what do we do in our main method? Let's make our thread. And then let's start the thread. Alright, so this is just an infinite loop right now. Okay, if I just run this and I look at top, I'm using 125% of the CPU with my Java command. Right? That's that tight loop that's just sitting there waiting for that flag to get set. Alright, so let's set the flag. So we'll let the user specify when to set that flag. So we'll prompt the user. We'll call next line, and next line will block until we hit enter. And then we're going to just say t.flag equals true. And then we'll say main program exiting, and we'll return. So we'll import. Alright, so what are we doing here? We make a thread, we start the thread, we'll ask the user to hit the enter key. Once they hit the enter key, we'll set the flag to be true in the thread, and we'll tell you that the main program is exiting. And the thread, once that Boolean flag is set to true, should kick out of this while loop and should say we're done, goodbye. Flag is called done. Alright, ready? So we'll go ahead and we'll run this. Our thread is executing. It's chewing up CPU time. This says hit enter to set the flag. We hit enter. It says main program exiting. But it has not exited. And our thread is still running. So something went wrong here. We clearly asserted the flag to be true because we printed out main program exiting, And once that done flag in the thread is set to true, this loop should exit. Alright, so something's wrong, right? Let me put a bogus print statement here in the middle of my loop, where I'm just going to print out an empty line. I'm not going to do a print line. I'm just going to print out an empty, zero length string. So we're not even going to see anything appear on the output. But if I run it now, it says hit enter to set the flag. It tells me the main program's exiting, and the thread says it's done, goodbye, and everything works perfectly. Alright, this can drive you a little crazy. This is one of these things that can happen with threads. And it's kind of hard to make this happen. This was a ridiculously simple loop, and even adding just a print statement in the middle is enough to make this bug go away. But if your code looked like this and there was a problem and you wanted to know if it was actually in the while loop, you might add a print statement, and as soon as you do that, your bug would vanish. And then you take out the print statement and suddenly your bug reappears, right? And that's kind of weird to deal with. Alright, so what is going on here? This while loop, while not done, right? Remember, this is a very small piece of code. And it looks like, up here it's going to read the value of the done flag and check to see if it's true. And if it's false, it's going to go back up and check again. Well, compilers optimize. Right? Reading from memory is relatively inefficient. Most computers, the PIC processor doesn't, but most computers have internal registers that you can access a lot more quickly than you can access memory. So, Intel processor, for example, has an AX register and a BX and a CX, and a VAX processor has a register R1 and R2 and R15 and so on, right? And rather than doing something like check done branch if not zero loop or branch if zero, right? Because this is an expensive memory operation. What you may find happens is before this loop something like move done into register 1, and then in here we're just going to say check register 1. And the compiler would make that decision, right, because it knows that you're going to use this variable a number of times, so it's going to put it in register 1. And any code in your loop that uses the variable done would be written by the compiler to use the register R1. And if you make a change in here to the value of done, right, that change would be made to R1 and written back to done and so on. But these are optimizations that the compiler does. Well, here's the problem. If we have a loop which is checking an internal register to see whether or not it's 0, and our main program is saying, let's go ahead and set the done variable in this object t. That done variable is, somewhere in memory. Well, that value in memory is getting set. But the while loop is not checking that value in memory. It's checking a local copy of done, a value that was loaded in, say, a processor register. And so we set the value in memory to be true, but our while loop hasn't noticed that. And this can happen. So when I put that print statement in there, right, when I came back from the print statement, I went back here and checked done again. That forced it to load done from memory, at which point it found that, oh yeah, done is true, and so now it said, well, not true, and that was false, and so it came out of the loop. Now, Java, we can force that to happen by saying a keyword volatile. So when we say volatile in front of a variable declaration, it says that variable should be read from memory always, because its value might change unexpectedly. It might change in a way that the code in here is not aware of. And so making that volatile is enough to make this work the way we expect. All right, doesn't usually come up, but it's something to know about. And it's also another example of where, you know, even though we're working at a pretty high level in Java here, there's ways in which we need to understand what's going on at the hardware level, at the processor level, processor in this case being the Java virtual machine, in order to make sense out of this behavior. All right, let's look at a different way to make threads in Java. So I've been doing this by saying, you know, define a class that extends thread. Okay, there's a different way that we can make a thread, something that'll run in parallel, which is to define a class but use the keyword implements and say this implements what's called a runnable. Okay, when we say implements runnable, it means we need to write a run method, and the run method can be, you know, whatever our usual run method is, whatever we want this thing to do in its own thread. And if we have a class like myThread3 which implements runnable, what we can do is we can construct an object of that type, and then we can use that object to construct a thread. So myThread3 implements runnable. Ant is an object of type myThread3. I can make a thread T1, and I can construct it by passing that runnable object to the constructor. And that gives me an object T1 that I can call the start method on. And it'll go ahead and create a new thread and then execute the run method in this object, which is, you know, set up the same way. So this looks exactly the same as if we said class my3 extends thread. It's just a different declaration up here. But when we want to cause this thing to execute in a separate process, instead of just creating a thread and saying ant.start, right, we create our object, we make a thread using that in the constructor, and then we say that thread.start. And so if we do this, we're making 3 threads, each of which will print out the numbers 0 through 19, and we get the usual, you know, behavior 0, 0, 1, 2, 3, 4, 1, 5, 2, 3. These threads are interleaving and running, you know, as independent entities. So that's just a different way to make threads. Now, why do we care about this? What's wrong with doing extends? In Java, you can only extend one class. Okay, it's something a lot of people don't like about Java. If I'm making something that extends a JFrame, I cannot also be extending a thread. So if I have a class that's extending some object and I want it to be able to run as its own process, my only option is to say, okay, this class also implements runnable. So I could say class myThread3 implements JButton, or extends JButton, implements runnable. So you'll see both of these. I almost always extend a thread just because it's one less step, right? If this myThread3 extends a thread, then I just say ant.start. But it depends on what you're trying to do. All right, that's it for this week. So next week's our last week. Monday I will go back and look at the URL class, and we'll see what we can do with that. We'll do some web access stuff to round out our discussion of networking. We'll talk about some Android. We'll talk about a few other things. We'll leave time last day or two to do some review and talk about the final, and then we're basically done. So we're well into the home stretch here. No more programming assignments, so congratulations on finishing all of those. I'll have office hours at 3. If anybody wants to talk about their code or anything else, you can catch me in about 10 minutes in my office. Otherwise, have a great weekend, and I will see you next time.